Year 13 Pure Maths Revision Video 7. This video features 2 questions on differentiation, a question on integration and a question on trigonometry. Some topics may be interlinked. So, first question, prove that this is an increasing function. So, an increasing function is a function for which f-x is greater than 0. So some functions will only increase for certain values of x, and it may be the case that functions increase and decrease depending on the value of x. So we've got to prove that this function has a positive gradient for any value of x, so it's always increasing. So f-x is equal to 3x squared minus 6x plus 6. That's the first thing I'm going to do, differentiate this. And then we're going to prove that this result is always positive. An easy way of doing that is by completing the square. So 3 brackets x squared minus 2x plus 6. First of all, factorising 3 from the first 2 terms, then completing the square, like so. Now, this always has to be greater than or equal to 3 because the minimum possible value of this part is 0, which is when x equals 1. It's a square factor multiplied by 3, so it's always going to be greater than or equal to 0. So the whole thing will be greater than or equal to 3. So f-x is always greater than 0 for any x. So, second question, we have some implicit differentiation here. You can see the function defined up above. So first of all, find dy by dx for part 1. So differentiating each term, we have 3x squared plus 3y squared dy by dx equals, and then we've got to differentiate this using the product rule. So splitting this up, I'm going to leave x alone and differentiate y to get dy by dx, and then swapping it over, I'll differentiate x to get 1 and leave y alone. Now, let's collect terms on either side. So I've got 3y squared dy by dx, subtract x dy by dx on the left, and on the right-hand side, I've got y subtract 3x squared, factorise dy by dx on the left, like so, and then divide through, giving you dy by dx is y minus 3x squared over 3y squared minus x, part 1. Explain why the expression cannot be used directly to find the gradient of the tangents to the curve at the origin. You can see at the origin, x obviously equals 0 and y obviously equals 0, and dy by dx is undefined because this denominator contains 3y squared minus x, and you cannot divide by 0, and 3y squared minus x would be equal to 0 if you substitute in x equals 0 and y equals 0. So part 3, P is the maximum point on the curve. The parabola y equals kx squared intersects the curve at P. Find the value of the constant k. So let's set dy by dx equal to 0, which is what would happen at P because we have a maximum point. So this tells us that y minus 3x squared over 3y squared minus x must equal 0. So this gives us y minus 3x squared equals 0. So y equals 3x squared. And if we're looking for a point of intersection with a parabola that's of the format y equals kx squared, well, this is only going to work if it's got the same equation as y equals 3x squared. So it's got to be k equals 3. And you can see that because if you set 3x squared equal to kx squared, it just becomes obvious that k has got to equal 3. So, an integration by substitution. It's suggested using a substitution here, although there are other ways of performing this integral. So I'm going to say u equals 2x minus 1, which means du by dx equals 2, and we then have this result here. So let's change our limits as well. And if x equals 3, then u is equal to 5. If x equals 8, then u is equal to 15. And lastly, as well, if u equals 2x minus 1, that tells me that 2x is equal to u plus 1. We're going to need that in a minute when we start the integral. So for my integral, my limits now become 5 and 15. In the numerator, we have 2x, which I'm going to replace with u plus 1. The denominator is going to be u, and dx is replaced like so. I'm going to pull the half out of the integral, and I'm going to divide both parts of the numerator by u. So this becomes 1 plus 1 over u du. And then we're going to integrate each term. 1 integrates to u, and 1 over u integrates to ln mod u. Although as both u values we're substituting in a positive, this won't matter. So evaluating this, for the upper limit we get 15 plus ln 15. And then for the lower limit we get 5 plus ln 5. And then before we multiply everything by a half, let's simplify what we have here. 15 subtract 5 gives us 10. And then we have ln 15 minus ln 5, which is the same as ln of 15 over 5, which is ln 3. But just to show very clear working, I'm going to put that there like that. And then multiply both terms by a half, so we have 5 plus a half ln 3, which is the answer that we were required to achieve. So the final question is a trigonometry question. We have an isosceles triangle ABC. We know this side and this side are equal, and angle ACB is theta. Use the cosine rule to write down an expression for AB squared in terms of A and theta. So for part 1, AB squared is equal to AC squared plus BC squared minus 2 times AC times BC times cos theta. So that's A squared plus A squared minus 2 times A times cos theta. So that's 2A squared minus 2A squared cos theta. Done. Part 2. D is the midpoint of AB. Use an expression for AD in terms of A and theta to show this result here. So, D is the midpoint of AB. Now, you can see this result involves sine and a half theta. So this is really setting us up to split the isosceles triangle into two halves, and to label this angle here with its value, which is a half theta. Now, we know that sine of a half theta is equal to AD, the opposite, divided by the hypotenuse AC, which is A, which tells us that AD is equal to A sine of a half theta. Now, AB is equal to 2 lots of AD, so AB is equal to 2A sine a half theta, and AB squared would equal 4A squared sine squared a half theta. I'm squaring and there's a square here. Now we have two separate results for AB squared, which we can equate to each other. I'm going to do that over here where I've got a little bit of space. So 2A squared minus 2A squared cos theta must be equal to 4A squared sine squared a half theta. And we can divide through all the terms by 2A squared. So this leaves me with 1 minus cos theta is equal to 2 sine squared a half theta, and we simply need to do a tiny bit of rearranging there before we get to the result that we want, which is that cos theta is equal to 1 minus 2 sine squared a half theta. which is this identity here. Now, the identity in part 2 is valid for all values of theta. However, the arguments in parts 1 and 2 do not prove the identity for all values of theta. State the values of theta for which the argument is valid. Now, the argument starts with an isosceles triangle where the angle theta up here has got to be greater than 0 and less than 180 degrees. You wouldn't be able to have a triangle with an angle equal to 180 degrees.